Hello and welcome to Toddcast number 63. So we're continuing on with aldehyde and ketone chemistry. And again, we're covering an area where we sort of covered this in the alcohol chemistry. So an alcohol can react with a ketone or an aldehyde to go on to form what's known as either hemiacetal or acetal if we use an aldehyde, or a hemiketal or ketal if we use a ketone. And so we're going to revisit that and then take it a little bit more in depth to some of the other carbonyl reactions that can occur with aldehydes and ketones in a similar way. So we mentioned in the alcohol lectures, in the alcohol podcast, that if you had an alcohol, the OR could attack the carbonyl and could form an OH here and then put the OR group on there. But if we use water, we actually get what's known as a diol. And a diol means two ols. And I want to emphasize just nomenclature. Organic nomenclature is an ever-moving target. And so there's two types of diols we're going to deal with in this chapter. And the one for now is known as a geminal diol. And so I want to figure out where the name comes from. And so, as with a lot of the terms we use in chemistry, they come from some, I don't know, base language, a Greek, a Latin, etc. And so if you know the term Gemini for twin, then geminal, they're both coming from the same carbon. Or if you happen to be fluent in a Latin-based language, let's say Spanish, for instance, gemelas and gemelos, GM, will be your diol. So when they're twins, they come from the same carbon, but when they are not twins, and there are neighboring carbons, and they are in the vicinity of one another. They are vicinal. And again, if you happen to speak a Latin-based language like Spanish, vecinos for neighbors. So they are neighbors, vecinos, or they're twins, gemelas. So just know that the term has some meaning, and if you have any ability to translate Latin roots or Greek roots in case of nomenclature, IPAC nomenclature, you're going to do quite well at being able to figure out what's going on in these reactions. So a geminal diol is what we're going to deal with now, meaning both OHs are going to be on the central carbon, which makes sense. It starts with two bonds to O. It's going to finish with two bonds to O. So we're going to look at acetone, a simple ketone, acetaldehyde, one H, and then formaldehyde, two H's. And when they form their various diols, it ends up, the more R group you have here, the more it hinders the O coming in. Just doesn't need to. The R groups donate in, so it's not as electrophilic, and the steric hindrance makes it perhaps a little bit harder to put those groups on. So it comes into play, but only about 1% is in equilibrium with the diol. It's predominantly acetone form. Acetaldehyde, you only have one R group donating in, so it's not going to be as big a delta plus, or I mean, it's going to be a little bit bigger delta plus. It's not going to be as stabilized a delta plus. So it might want to come in and attack more, and H is small enough that there's less steric hindrance. So the water's going to attack a little bit more, and you end up with about 15%, 14%. And then finally, when it's two H's, there's no R groups donating in, so it's the biggest possible delta plus. The water's going to attack more readily, no steric hindrance. So you end up predominantly, almost exclusively, the geminal diol. And what this means is formaldehyde reactions are not as clearly carbonyl reactions as acetaldehyde, long chain aldehydes, or ketones. So the carbonyl chemistry we talk about has to be in the carbonyl form. Formaldehydes do their own types of reactions, and so they can form oddities where they can actually attack themselves. So if water attacks, that O minus can attack another formaldehyde, and they sometimes form trimers. So you can just see formaldehyde doing strange things. It generally doesn't stay as a carbonyl, whereas the rest, the aldehydes, long chain aldehydes, and long chain ketones have a tendency to stay as the carbonyl form. Okay, so we have this equilibrium, just something to consider. Want to look at the mechanism because guess what? The mechanism is so common that if you know it for one, you kind of know it for all similar reactions. So look at this under basic conditions and then later in acidic conditions. So under basic conditions, I have this compound. I'm going to add an OH minus. Again, negative and neutral for basic conditions. So nucleophile can come in and attack. There's no H's in deprotonate because they're on the carbonyl. It has to be an alpha carbon here. So it can only be a nucleophile. It's going to come in and attack. So under acidic conditions, we said protonate, break, make, deprotonate. You must deprotonate water to get this. So deprotonate first, followed by make, the opposite, and break. So under acidic conditions, we do break, make. And then last step, deprotonate to get this, make, break, and then protonate here. Cannot add acid, has to be neutral water. So this comes in and attacks, regenerates the OH minus. And ta-da, you have the geminal diol, two H's on the carbon, and regenerated OH minus you started with. So OH minus is catalytic in this, and water is your actual reactant. So it's water plus formaldehyde going to geminal diol, and OH minus is a catalytic form. Under acidic conditions, okay, similar, but rather than attacking carbonyl, we now protonate the O and make it even more electrophilic. So this time we have an acidic water, that's going to come and pull off an H. When it does, you'll now have this protonated form. Because of resonance wanting to come and stabilize that negative or positive charge, you're going to create a positive charge on carbon. That carbon is going to be far more electrophilic, so water is going to readily attack it. So you have, let's see, protonate, break, make, and then water comes in to deprotonate. So here's my compound right here. There's the water coming in. It's going to take off a proton. Can take off either one, but deprotonate. So your mechanism, protonate, break, make, deprotonate, or deprotonate, make, break, protonate. Okay. So pretty straightforward mechanism that we're going to see over and over and over. So make sure you can just see the pattern and you should be in good shape. So we will consider a mechanism we looked at earlier. This is the same thing as we did before, only now it's a ketone instead of an aldehyde. And instead of one OH, there's now two H's on the compound. And we're going to form the protected form of the ketone known as the ketal. Okay, if I add water, it pushes back this way. If I add the diol, it pushes it this way. Heat it up and dry water off, you're going to end up getting the ketal. The mechanism again is protonate, break, make, deprotonate. Under acidic conditions, PBMD. So you're going to follow the same pattern. Protonate, the most basic site, and that's usually what you do. Occasionally you're going to protonate a different site, but most basic site, the O, you protonate the O. And so I'm going to put the lone pairs in to specify what's going on. That lone pair is going to attack. You know, one lone pair left. So protonate's done. So break is next on the agenda. You're going to break the pi bond. It's a resonance structure. So that is why it's a double-headed arrow. Next on the agenda is going to be make. It can be either OH. So lone pair here, lone pair there, lone pair here, lone pair there. One lone pair left on it. One lone pair, one lone pair. So we've done make. Last but not least, deprotonate. Our acidic proton is right there. So deprotonate, it's going to come off. I'm going to be a little more specific this time than I was last time we did this mechanism in a previous podcast. I'm going to make it so that this compound is the one that actually comes and takes it off, or this compound is the one that comes and takes it off. So it's got to be something taking it off. I have it magically falling off. Some chemists will be very upset at that. So in that case, I'm going to choose either this compound or this compound, the ones that are in solution to do this. Reality is, it's a random collision. Whatever's taking it off is not necessarily 100% of the time going to be the ketone or 100% of the time going to be the diol. It can fluctuate. So that's why I don't mind the magic H falling off to oblivion. But if you have a professor who's very upset about it, then put the compound most likely to take that H. Okay, so protonate, break, make, deprotonate. I'm only at the hemi. There's still an H here, so it is only in the hemi state, so I'm not done yet. So I have to do 4 more rounds. Protonate, break, make, deprotonate. I want to get rid of this OH, so I'm going to protonate there, even though I could protonate here and go backwards, could protonate here and have this attack it, but this is your most likely protonated site. So protonate. So protonate is done. Next is break. So we're going to break this by having this leaving group leave. So break is done. Make. Intramolecular is very fast. It's going to attack. And then finally, deprotonate. So your last step, your deprotonate is going to just simply have that H again magically fall off, apparently. And again, I am okay with that. It could be a carbonyl coming in, could actually be this OH coming in and getting it. We have different possibilities in solution of things that can take it off. So as more and more things get in solution, it's going to get a little more complex. So that's why I am perfectly fine with not having that in there and not having anything taking this H off. But again, you need to adhere to whoever is teaching your class what their preferences are. Okay, so carbonyl mechanisms in general. Really important to get this down to an art. So they're very similar, and you're going to see it a lot. First semester, a little bit. Second semester, a ton. Ketal formation that we just did. You protonate to form protonated carbonyl. It breaks to when it forms the resonance structure. Make when something attacks, and deprotonate to make it neutral. And you end up with a hemi. You then protonate the OH to make it a leaving group. It leaves by breaking a bond. The other one comes in, or another alcohol comes in to make, and you end up deprotonating. So I probably am going to change my outcome here to match the intermediate, because we just did the other one, although that's fair game as well. So OR and OR. Oh, that looks terrible. Let me be so bold as to just get rid of the OR altogether and make it look a little better. Okay, so you have ketone, the hemi-ketal, and the ketal. Okay, ketal hydrolysis, meaning you can do the exact same thing backwards. So perfect. I can protonate, break, make, deprotonate to turn it hemi, and then take it all the way back. I'm going to, in this case, go in the opposite direction, going to make it so that it's a second reaction. So that is your OR group that's coming off. And this is going to be, it's now off and by itself. So I've left out the intermediates to simply point out protonate, break, make, deprotonate, protonate, break, make, deprotonate, and you end up doing what you need to do. Ketone to hemi is 1 round, hemi to full, second round. Ketal to hemi, full round, hemi to, I'm sorry, ketal to hemi, full round, and then hemi to ketone, a full round. Protonate, break, make, deprotonate under acidic conditions. So this is acidic. That's why protonate is first. Acidic, protonate is first. Transesterification, we're going to look at one of those right now, coming up. But it's going to be the same thing, only this time we aren't going through hemi. We're now going through 3 bonds of O. So 2 bonds of O and a double bond and an OR. We now have the OR still on there, but now we have an OH and a different OR from a different alcohol. And then in the end, we get rid of that OR. So want to emphasize, I don't know if it's coming out cleanly in the picture. I want to emphasize this OR is an OR prime. This OR is a regular OR that represents different ones. So this might be methyl. This R might be ethyl. So note that there is a slight, gosh, it's hard to see, but there's a marker here, meaning it's this new one going on and that one going off. But again, same story, protonate, break, make, deprotonate, protonate, break, make, deprotonate. It's an acidic condition mechanism. The same mechanism over and over and over. So hopefully this seems, I don't know, easier to you. It's nice and organized. So here's the mechanism in its entirety. So notice I've hopefully done a better job. This is a prime, this is a double prime. The prime is coming off, the double prime is going on. You're transferring one alcohol for another. How this becomes useful, there are so many shuttle reactions that move things across our cell membranes, and a vast majority are trans something. So if you have an alcohol and you want to get across the membrane, you can take the alcohol you want to get across, turn it into an ester. The ester can transfer across because now it's a bulky alkyl group. You can go across the cell membrane, and then once it's on the other end, you can remove it and turn it back into the alcohol. Equilibrium constant to go from an ester alcohol to an alcohol ester. You have an ester and alcohol on each side. So equilibrium is around 1. So delta G is around 0, which means it's reversible. So we don't always need a favorable reaction. A transfer reaction, where you convert it to one thing, move it to somewhere else, and then take that group off, is very helpful. So transport mechanisms, a lot of times will have trans esterification, transamination, trans something, and a reversible reaction with a carbonyl. Very easy to do. First step, protonate. Protonate the O. Carbonyl is the most basic because those electrons can donate in. You then break. Again, it's a resonance structure, so it's a double-headed arrow. Double arrow, I guess I should say. Protonate break. Next step, make. That's where your other alcohol is going to come in. And then deprotonate. Get rid of the H on here. Okay, one round done. The next step, the protonate could go on any of these 3 sites. They're all going to be roughly similar. I mean, OR is going to be a little more basic than OH. Steric hindrance might make the OH a little more favorable than a medium R or a bulky R. But now is that case where I don't worry about which one's more basic. I worry about which one gets me what I want. So you want the ROH with the prime to leave. So I want that one to go away. So mechanistically, that's one I need to protonate to make it a leaving group. The one I want to lose has to be lost. So protonate. And if I would have chose here, I would have gone backwards. So I would have gone here. It would have been a different pathway. This is when I protonate. Break means the leaving group is going to leave. Make, the resonance structure kicks in again. And then deprotonate. And again, H's in my mechanisms magically come on and fall off, and I am okay with that. And I know I emphasize this over and over, but if you happen to be watching these and you're not taking class that I'm teaching, then keep in mind you want to follow whatever your professor or your textbook's habits are, and some don't let H's magically come off and go on. But considering I do not believe we are small enough to get into a flask and see what every single H is doing, I think it's a little bit kind of presumptuous to say we know that the H goes specifically with one thing or another. So I know where it has to go within the molecule, but I don't know where it comes from and where it goes to after the reaction. Okay, so natural hemiacetals and acetals. Why is this so important to us? And it is absolutely biologically and biochemically massive, incredibly important. Well, glucose can have a straight chain form, that's one form, but you can also have it close on itself. And so for whatever reason, this OH is the OH of choice. The penultimate carbon, so carbon number 1 is the most oxidized, the aldehyde, so 2, 3, 4, 5, 6, so 6 carbon structure. Penultimate is the 5th one next to the last. That hydroxyl is the one that's going to attack. When it attacks, it's going to form a 1, 2, 3, 4, 5 carbon and 1 oxygen ring, so a 6-membered ring. So you end up with this structure. So OH could attack, but the steric favors the one that forms the 6-membered ring. So you end up with this. Notice that this carbonyl still has 2 bonds to O. They're both marked in red. And this OH is pointed down. So the pointed down one is the alpha diastereomer, the alpha anomer as it's called. The OH could also be pointed up. It ends up OH down is a little more reactive, and for sugars, we're going to want them in a reactive state, so we typically, that's when it goes down. So random point of interest, just something to add to your arsenal of information. The first step of glycolysis is to phosphorylate a, a sugar, and you phosphorylate in a way so that it sort of locks it into the cell. So once it turns into a ring and crosses into the cell, it transfers an alpha. We phosphorylate it, and it phosphorylates only the alpha because that's the one that's going to be more reactive down the road, so that it cannot, it's too bulky to go back through a transporter. So a transporter can move the glucose from outside the cell to inside the cell. First step of glycolysis, we phosphorylate here. So it becomes 6-phospho glucose, and it's the alpha form that gets selectively treated. Okay, but note that this is an hemiacetal, has an OR and an OH. So the open chain is a linear form. This is your hemiacetal. Hemiacetal is the most common form. Okay, galactose. So galactopyranose means 6-member ring, comes from galactose. This is glucopyranose. It's glucose. Notice the only difference is carbon 1, OH there, carbon 2, carbon 3, carbon 4. So they're different they're diastereomers, or more specifically in biochem known as epimers of one another, CO4 epimers. But if these two combine, this H and this OH, this is a good leaving group, that's a good group. Those two can conform. It's not going to be water anymore. You're going to lose that water and just have an O. You have lactose. So lactose is a galactose bonded to a glucose with a 1-4 linkage. So carbon number 1 on one side, carbon number 4 on the other. The key thing, this is an OR and an OR. So this is an acetal linkage because there's still an H there, so it comes from an aldehyde, but this is an acetal linkage. So absolutely, positively important to know that. And then last but not least, here's your acetal linkage in just glucose connected to fructose. This is known as sucrose. So you have one acetal linkage here, and this actually, well, it's an acetal linkage on one end. It's a ketal linkage on here because that's a C, and there's a H here coming up. So I'm drawing that one H there. So it's an acetal linkage on one side, it's a ketal linkage on the other side. So it has both an acetal and a ketal. Okay. One more, and then I've probably overdone it, but on the surface of protein, you will sometimes get a glucose with an NaCl, so an NaCl glucose, connected to a galactose and an L-fucose. And this is the antigenic marker for blood type O. So if you're a type O, I happen to be a type O. So if you're a type O, then you have these 3 sugars. If you were type A, you have an extra galactose here. If you're type B, you have an extra galactose with this NaCl on it. If you're type AB, you have both those extras. But O is a universal donor because it has the 3 common sugars. So you donated A or B, there's nothing foreign, but it can only take O because if you have another sugar on here, you have a foreign body, your antigenic markers will recognize it as foreign and reject it. So you cannot take it. If you're type O, you can only take type O blood. But if you're type AB, you can take everything. If you're type A, you can take A or O. And if you're type B, you can take B or O. But these are the various linkages. So the linkages we have is carbon 1. So it has an acetal linkage because there's an H there. This has an OR and OR, so this is an acetal linkage. And this one right here, OR and OR, acetal linkage. So all CAs represent carbons that are in an acetal linkage. Just like a carbonyl, it has 2 bonds to O. Just like carbonyl, it has 2 bonds to O, 2 bonds to O. So it still must have 2 bonds to O, but no longer a pi bond. Okay, lots of information. There's a lot there, a lot of bioinformation. And as you can apply your OChem to bio and your bio to OChem, it will hopefully become more interesting and more memorable. So thank you for hanging out for another podcast, and I will see you at the next one.